Good morning, students. I hope everybody's doing well today. I've had good luck with the audio of late, so I assume that everybody can hear me. What we're going to do today is we've completed the work on the polynomials, so that's actually good, but I hope that you were able to maybe fill in some details that maybe you didn't have in your previous course, or maybe you're able to think about things a little bit differently. You'll use those techniques quite often in calculus. And so at times it might seem a little bit odd the way we work with polynomials and the theory of equations. So hopefully that's helped you to solidify what you know, and then also to become more confident. Today, we actually are going to start a review of the exponential and logarithm functions. And this is actually simpler material than the theory on the polynomials. Most students find that they remember more about exponential functions and logarithms than they do the polynomials. So hopefully that'll be the case for the class. So what I want to do today is basically present some review material on the exponential functions, and then segue into the logarithms and some of their identities. And then on Thursday, we can use some of the identities for the logs and those properties to actually solve some equations. So this will be a nice review of your college algebra work. So let me go ahead and share the screen. I'm going to use the Google Calculator today just as a method for approximation. Again, we always assume that the answer is to be exact in WebAssign, but there are opportunities where the WebAssign will actually want you to provide an approximation, even if you've already provided an exact answer. So I'm going to show you how to use the Google Calculator as a tool that we have for the lecture today. Now, what I wanted to do was just give a brief overview of some of the ideas that we're going to have in the exponential functions. And I have, let me see if I can locate this. I've got a nice summary of some of the laws of exponents. Let me find that because I want to share that with you. I've got it written right here on that page, but I've got a nicer page that I want to share with you too. So when you started your college algebra class, you did some work like we did with, the equation solving, and you talked about one-to-one functions where you could basically prove that a function was one-to-one. That is, you didn't have to kind of punt and think, well, I guess, everybody's telling me it's one-to-one, I'll just believe it. Now, when we actually start talking about exponential functions and then the examples where we can morph that into some compound interest, I want to say this. In calculus, we will actually begin, when we get to the end of the course, with the natural logarithm and be able to show using techniques of calculus that the natural logarithm is one-to-one. And that will be the beginning of then getting the natural exponential, which will be the defined inverse. And then from there, working all the calculus into the natural log by using change of base. But we don't have any of that detail with us now. So what we're going to do is what you basically did in college algebra. We're going to start with the base A exponential, and we're going to make the assumption that we have a one-to-one function, and then utilize those properties. And then when we get to calculus 1, we'll be able to nail all of this down in a more precise way. But this doesn't leave us in the lurch at all. We've been able to do some really good math with our limited ability right now. So what we want to first start out with is a base. And so this is all just preliminary review. We have a base, which we will usually encounter the letter A. And if we need a B, we'll use that later on. And we want the A to be a positive number And we want it to be non-unity. That is, we don't want it to be 1 because that's not a very interesting base. So we call this base A. Now, what we want to do is define the base A exponential, at least in an intuitive fashion, where we can actually work with it. And so we're going to have f of x equal to a raised to the power x. So when we think about an exponential function, we think about something that's similar to the power function, but very different in other aspects. As opposed to the power function, the base is actually fixed, and the power or the exponent varies. So this is a very different object from the power function. The power function is actually an algebraic object, whereas the exponential function is a transcendental object. And we'll say more about that as we work into trigonometry. And so one thing we can do with our limited definition here, we will define this for all real numbers. So we're going to say that it makes sense to take a positive real number and raise it to any power. And considering power functions, that's certainly not something that would make us fear that we're going to get inconsistency. That's a legitimate operation in mathematics. And so what we found in the college algebra cases is that if A, the base, were bigger than 1, then clearly the powers here, that is, we raise A to larger and larger powers x, the outputs get larger. And so we got this nice increasing function. However, if the base were between 0 and 1, like maybe 1/2 or 1/3, the outputs actually got smaller. Again, agreeing with our intuition, taking a number between 0 and 1 and raising it to larger and larger powers will make the output smaller. So when we make a comparison between the two, the only difference is one is increasing and one is decreasing. So what we have now is a new parent function. Just like we had before with the transformations that we can move around, we can reflect in the axes, we can stretch and compress horizontally and vertically, and we can shift it around. So we can do all the things that we did with the other parent functions with these new exponential functions, or maybe somewhat new exponential functions. But I did want to just make a few allusions to some of the properties that we're going to enjoy with the exponentials. Just like the rational and the polynomials, they are smooth. That's going to be what we have to use or verify in calculus. But when we draw these functions, they're going to be nice and smooth. No jagged edges, no breaks, anything. And as I say, no breaks, also continuous. In calculus, you're going to prove that a function that's differentiable is automatically continuous. And so this is, for instance, if I say smooth, I automatically get the continuity. But that'll be a result that you'll learn in calculus, and we'll be able to prove that relatively quick after you study limits. Another thing that's interesting about these functions is as x passes to negative infinity, or x passes to infinity in this case, the actual outputs get closer and closer to 0. So we get a horizontal asymptote, but it's not in the sense of the rational function. That is, when we do the rational function, we let x pass to infinity, and then we look at the degrees of the numerator and denominator. Here we don't have that, but we still have a horizontal asymptote, y equals 0, the x-axis. In this case, again, as x passes to negative infinity, the outputs get closer and closer to 0. Here, as x passes to infinity, the outputs get closer and closer to 0. So we look at the standard exponential function as a positive output function. So when we think about the range, we run from 0 to infinity. We never hit 0. Exponential functions are never 0 unless, we shift them around and we create an x-intercept. But the standard functions, as we've written here, are always positive. And then, of course, by the way we've defined it, the domain is all real numbers. So again, we're going to get a y-intercept of 1 in both cases. that is the ordered pair corresponding will be 0, 1. And we are going to feel comfortable at this point that the outputs either get increasingly larger or decreasingly smaller in a very uniform way that makes the function 1 to 1. And because it's 1 to 1, ladies and gentlemen, it is therefore invertible. It has an inverse function. So I'm not asking you to believe anything that at least doesn't have some intuitive basis. But until we get to calculus, we won't be able to rigorously justify the 1 to 1, and we'll do this in the opposite order. Unfortunately, if I had to change some things, I might do the natural log first, but my experience has shown that students tend to do a little bit better when we start with these functions. Now in calculus, of course, we'll flip that around, but you'll be mature math students by then and it won't matter. So what I've done here is just give you a brief introduction review to the exponential function. And before I go to the next material here, what I want to do is I put on an extra sheet here the laws of exponents. Now, when we deal with power functions, we have the power rules, which we, again, use often without even thinking about them. And the similarity here between the exponential functions and the power functions is rather large. So we can look at some of these rules, though we can prove some of them, others we will take as definitions. And I want us to be comfortable with these and use these as we need. So what we're going to assume, at least for now, is that the powers or the exponents, x and y, will be real numbers, and we have a base a. Again, it doesn't matter what letter you use for any of these, but these are fairly standard notations. Then we're going to have some rules that remind you of the power functions. With the same base, if we multiply a to the x times a to the y, we can actually prove this, and we will do this in calculus. We actually add the exponents. So the idea here is that if we have extra time in this class, we could actually do this in the rigorous way if I assume some calculus. But just like with power functions, as you multiply two power functions with the same base, you add the powers, so to speak. So this is a rule that should be very comfortable for all of us. And if you like, you can think of x and y right now as just positive integers to make this easier to see. Now at this point, we have another rule that we have with power functions. That is, if we take a to the x and we raise the a to the x to a power, we do just like we do with power functions. We multiply the two exponents. Like x squared squared is x to the fourth. 2 times 2 is 4. So we say x times y to get the new exponential function. So these very much parallel what we think of when we do power functions. Now, the next two, when you see the 3 dashes here, ladies and gentlemen, that just means that we're defining something, and we're not really proving it. We're saying that the mathematics supports this. And like we had before with x to the 0, we're going to define a to the 0. As long as a is not 0, which it never will be by definition, we're going to define this to be 1. And again, I'm going to write this as a definition. So a to the 0 power will be 1, and it will be consistent with what we have defined here in 4 and also the theorem number 5. Now, one thing I did over here is I wrote down some notation. When you think about a polynomial and you think about the constant term, when we look at this, we think, well, we could really put x to the 0 beside the constant term because we define x to the 0 to be 1. And then we have the x term, and then the x squared term, and then the dominant term, which is the x to the n power term. So we're thinking the same way here. So if you want to think about polynomials in x to the 0, that would be a similar thing as we had in 3. Now, another thing that we use quite often is the definition of the negative power. That is, x to the negative 1 is actually defined to be 1 over x. And that is consistent with the way we work with algebraic objects, where we're going to have the same definition for the exponential. And what I've done here is I've written it in a way to make it seem a little bit more plausible. For instance, we can say a to the negative x and use this rule number 2 and just write this as a to the x raised to the negative 1 power. And then the negative 1 power will actually reciprocate like we do here, and we get 1 over a to the x. Now, if you want to leave out the middle step, you can just say a to the negative x is just 1 over a to the x. So basically, we get reciprocation just like we get here, but again, looks just a little bit different because we have that a, the base, and the power. So this is a very convenient definition here that basically aligns with this definition for the algebraic object x to the minus 1 as we flesh out right here. So again, 3 and 4, put those in your toolbox because we will definitely use these when they are beneficial to our calculations. Again, we make definitions that are consistent with the theory that we already have because we need them. We can't do without them, and then we get to the point, if we don't make the definition, we're going to eventually force to make it. So we're kind of between a rock and a hard place. Now, the very last one, again, mimics the power rule for quotients. When you divide a to the x by a to the y, just like with power functions, you subtract the powers. So we're going to say the new function, like we have in 1, will be a to the x minus y, where we subtract the powers. So you're thinking, isn't this really a special case of this? Because you could write 1 over a to the y is a to the minus y, like you have here. And then you add the x and the minus y and get that. So you can actually come up with ways to justify a lot of these just by using previous results. You're thinking, is it kind of a waste to write this one? Well, not really, because it's convenient to actually think of multiplying exponential functions and dividing them just for convenience and notation. And though we like to be very efficient in math, sometimes the redundancy is actually useful, and it just makes us feel a little bit better. So the idea here is that I want you to put these on a note card. You probably already know them, but have them on a note card for easy reference so that you can use them. And lots of times when you're working problems in this chapter, these will be the ideas that will push you to the next step with confidence. Okay, so these are the laws of exponents. And of course, I cheated a little bit. I went ahead and wrote down the inverse function. I'll say more about that, the base A logarithm, but that'll come later. I just wanted to make this complete. Now, I wanted to mention, lots of you, when you take your college algebra course, your professor will say, okay, well, now we're going to do some interest problems, but basically these are just exponential functions. So you remember this formula for compound interest from college algebra. And why is it exponential? Well, if you remember what all these formulas or all these letters mean, we have an amount for a transaction. We have a principal investment P. So this is a one-time deposit. It's not an annuity like some of you may be aware of when you finance a home or a car or your credit cards. Annuities are great for making money, but annuities help businesses get a lot of money from you, which is not what we want. So the annual rate of interest, R, is a fixed number. The number of compoundings per year, say maybe 12 times per year or 2 times per year or whatever, is another fixed number, and 1 is fixed. So what we see here is that this positive number, 1 plus R over N, is a base, and it is raised to a power. That is the T, the T is fixed, but the N varies. and the t varies. So we get a quasi exponential function. And so just like we have up here, we would say, well, let's evaluate this function for different powers here, for different values of n and t, just like we would do for this function. So here's our base and here's our power. So this is an exponential function, but it looks a whole lot different from this, a little bit more complicated. But this has all the nice qualities of the exponential function. And so that's why you find this particular example when you study exponential functions. So what I want to do is do it a little example with this and show you about the Google calculator. Now, again, it's good to kind of get your feet wet and get accustomed to using these exponential functions again, because we've been doing all these polynomials, which are very different. So remember, we have A equals the principal times 1 plus r divided by n raised to the nt. And here's an example. I just wrote this again, so we'll have this on the page so you can see it. And we have a principal of $3,000, and we have interest compounded monthly. So these are very easy, but again, these are rusty. So we want to go through some of these. Compounded monthly, and we have a duration T of 6 years. And we want to compute the amount, compute A, if the annual rate of interest is 4%. So this is a very straightforward calculation. First, what we're going to do is we're just going to write P is 3,000. And then, of course, compounded monthly, that will be N is equal to 12. We obviously have T is equal to 6. And then, of course, R we can write as a fraction. This will be 4 over 100, like we're doing the mixture problems. And then, of course, divide by 4, we just get 1 over 25. So now this implies that the amount, we'll just go ahead and fill in our formula, our exponential formula. So we have 3,000, and then we have 1 plus, again, 1 over 25 divided by 12. And then we have the n and the 6. So we have 12 times 6. Now let's go ahead and reduce this. So we have 3,000. And then we have, again, 10 times 25 is 250 plus 50 gives us 300. So 1 plus 1 over 300. And then, of course, that'll give us a 72, 60 plus 12. And then we can get a common denominator of 300. So we get 300 downstairs, and then 1 plus 300, which is 301 upstairs. So what I've said before, we basically have the exponential function here. The base, in this case, is 301 divided by 300. And the power that we're trying to find is 72. Now this right here is exact. So now you can see that this is actually exponential. That's exactly what it is. And we're stretching it, and then we're thinking, well, how do we do something like this? Is this really a calculus problem? Absolutely. This is what you can see here. This is derived from the binomial theorem. We can think of this as a binomial, and so we need the calculus to actually do this. I mean, of course, you're thinking a computer could just multiply this 72 times, you know, and you'd be done, but the computer uses the calculus infinite series. And so what we would need to do at this point is to get a good approximation. WebAssign will say something like, in this particular case, they say round to the nearest cent. That will be the formatting, round to nearest cent. And you will need to follow the format. And so what I want to do is show you the use of the Google calculator that we have here. So let me do the share. And we'll go to the Google calculator. Let's see, I think, oh, let me get rid of some of this stuff. Let me move some of this stuff down and move all this other stuff to the side because it won't see everything. This Zoom has a mind of its own. So let's try this. Let's see here. So let me get rid of that. And let's see. Oh, yeah, I can almost see it. One more time. So let's get it here. There we go. So this is what I'm talking about, the Google calculator. Free is the operative word. You can just do Google Calculator Scientific. And this is a nice tool when you're doing exponential functions and logarithms, especially when you don't have nice numbers. And also you've got nice trig functions here too that we're going to be able to use. So now we can say, okay, 3,000, we need a nice approximation here, times, and we'll just use our parentheses. We'll say 301 divided by 300. And then we can close, and then we can use our exponent key. That'll put a little box right here, and we can input 72. That's a simple number. We don't need parentheses. And so now the Google calculator will give us a nice calculus approximation of 3,812.225. And so what we're going to do is we're going to round to the nearest cent in using the standard rounding procedure. So this will be 3,812.23. So the idea here is you can clearly use a handheld calculator or whatever, but the Google calculator is very nice and it's right here on your computer. So again, just like you always do, you want a nice exact calculation. I don't like to see decimals hanging out unless you're just kind of forced to work with them. Your calculation should be neat and clean. And then you can see the mathematics at work as opposed to just having a bunch of numbers hanging out that is prone to much error. Note here that when we do this calculation, it is exact to this point. And if we need an approximation, we can do that with confidence, knowing that we don't have any round off error. If you don't proceed this way, you get round off error, and that is not what we want. Okay, now let's do one more example, just so you'll be comfortable with this. We can take this particular formula here and actually solve for P. So for instance, solve for P to compute present value. Solve for P to compute present value. So for instance, we might be interested in knowing what kind of deposit we need to accrue a particular value in the future. So now you can see here that P would just equal A divided by the exponential portion. So this will be 1 plus R over N to the NT. But of course, now we can use the laws of exponents and write this with the negative power. We don't have to. You could certainly leave it this way. But we have 1 plus R over N divided by, well, excuse me, 2 raised to the negative NT power. So this would just be maybe a little bit more convenient. Each of these are fine. Maybe you would prefer having no negative powers, but this is an equivalent expression. And so now here's an example from your WebAssign. So we want to find the present value of $10,000. And what we're given if interest is paid at 8% compounded semi-annually. That's twice. Compounded semi-annually. Semi-annually for 2 years. Again, a very simple computation. And so again, let's just focus on the fact that N will be 2 and T will be 2. And then we have R is 8 over 100. So we can divide by 4 and get 2 over 25. So now we can use our formula, fill in all the details. So P will now be A, which will be 10,000. Kind of fun to do these calculations, you know, now that you have a better insight about symbolic computation. Your work should be clean and neat. We strive for that as future STEM professionals. That should be your goal. So we have 1 plus. Now we have the R, which is 2 over 25. And we divide by N in this case, which one ever you like. We'll just use this one, which is also 2. And then we have negative. We've got NT, 2 times 2, which is 4. So we can clean this up a little bit. So we have 10,000. Now notice the 2's absorb, and we just have 1 over 25. And then, of course, we can get the common denominator of 25, and that'll be a 1 plus a 25, which is a 26. So we get our exponential function. So now, ladies and gentlemen, this would be our exact value. But of course, you know, our banker will say, okay, you know, you're their client, and they say, well, this is the exact value that we need, but let's go ahead and get an approximation of this. So we can go back to our Google calculator. So I'll share this. So now with the Google calculator, you just hit the clear, and it does keep a log of everything you do. So now we can have 10,000, 4 zeros, and then we multiply. Now at this point, you can use your parentheses, 26 divided by 25. Again, this is where the binomial theorem is allowing this calculator to work. And then, oh, I don't need a full report of Norton Antivirus. They love to tell you that they're doing a great job for you, but they use all the resources of your computer, but I put up with it. So now we want a -4 as the power, and we want to include that in parentheses to make sure it reads the negative with the 4. And that will give us 8,548. And then 0419. Now these are some really odd rounding in this case. What they want you to do is round up. They don't want you to round down. So the formatting in this case was round up to the nearest cent. Round up to nearest cent. Now I keep getting messages from everyone, and maybe not so much from this class, but you ignore the formatting, and then you wonder why your answers are wrong. Well, because you're not following the directions. And ladies and gentlemen, it is imperative that you read the formatting and that you use exact computation. If you need to use a symbol like the pi or the natural base E, then you must use those symbols. E on the keyboard will stand for the natural base, but you have to use the Greek pi for pi. So now this will imply $8,548.05. So let's go back to the document cam. So we use our Google calculator and then we round up to the nearest cent because WebAssign asked us to do that. So again, we can see that if we want our future value to be $10,000, we need a present value investment of this amount. So again, you can do lots of nice calculations with annuities. Some of you may end up combining, a business degree or a master of business degree with your engineering degree, and that's a good way to go to make yourself more marketable. I think what's good about STEM is that it opens the doors to so many different careers. And if you actually, like I said before, end up doing your own business, this will be very useful. Now, what I want to do is just share a couple of things with you before we get on to the natural base and talk about continuous interest. I just want to do a simple example using these new parent functions. Now, once you see one, you're done. I mean, the logarithms will be easily drawn using the exponential function. So I want you to be comfortable with considering a parent function that's an exponential. So I'll just say graph using transformations. So we want to graph using transformations. So now what we see is the parent. The parent is our standard exponential 5 to the x, and we know what that looks like. So what we want to do is break this down just like we've done the others. And so you can, again, you can make these up. We can be much more complicated or even easier. So when we look at this, what we first want to do is write the parent function and then just create h of x. So we can see now if we apply the negative, this will be an x-axis reflection. And we're thinking, what objects do we have on the parent function? Well, we've got the coordinate pair, which identifies the y-intercept, and we have the x-axis. Now, of course, we could put in another point if you like. We could do what, 1, 5, just to throw in another point if you want. We don't really need it, but just that's an extra point on the curve, which is easy, and we don't have to worry about any approximations. So this is going to give us negative 5 to the x. And then, of course, adding the 7 will just be an upward V shift. So very simple, upward V shift. Of course, when we do the trigonometry, we're going to spend a lot of time with horizontal and horizontal compressions and changing periods and things. So that'll be a little bit more complicated than this, but certainly doable. So this gives us 7 minus 5 to the x. So what's happening with these objects under the x-axis reflection? Well, of course, the y's become negative, so we get 0, negative 1. Of course, the x-axis is just reflected in itself, so that doesn't change. And then, of course, we get 1, negative 5. Now, of course, if we do an upward V shift, we add what, 7 to everything. And I want to say upward V shift. I'm sorry, I left that out by 7. I just thought, well, I guess you'll just stick that in there and not worry about it. Let me check the magnification and the focus. That looks good. Now we're going to add 7 to everything. So that's going to give us a 0, 6, y equals 7, and then 1, 2. So now we have a new horizontal asymptote, and we've got 2 new points that, and then of course we know what the shape will be. So let's go ahead and graph our reasonable estimation. again, with polynomials, we don't have to plot 500 points. Even with rational functions, we don't have to plot lots of points. We just want to be able to get a reasonable graph. So now we see, okay, well, do what, 7? So we can do 1, 2, 3, 4, 5, 6, 7. Kind of crude, but we've got plenty of space to work with. So that at this point, this is easy compared to what we've been doing. So you get a little bit of a break. And then of course, we've got the point 0.06, which is right here. And then we have the point 1,2. So let's go ahead and mark this. So this is gonna bow down quickly. So we can draw it. Don't have a lot of space here. I should have spaced it a little bit better so it looks nicer, but we'll survive. So here's our exponential function. So we've got 0.6, and we have 1,2. So this is our h of x, our cheap graph for little or no work. Now, one thing that we notice here, and this is kind of a bridge to what's to come, you already actually know how to do this, but notice we cross the x-axis here. And so we're thinking, you know, what is that point there? And so we think, okay, well, that would just be an x-intercept. H of x equals 0, and we're professionals at doing this. So that would mean what? 7 minus 5 to the x equals 0. So equivalently, we have 5x equals 7. And then, of course, we're thinking, well, you know, we'll talk about this in a few minutes. We'll say, well, okay, what's the logarithm? It's a power of the base. So for instance, x is a power of the base. So it's a base 5 logarithm, and explicitly, it's the base 5 logarithm of 7. So we write this in the corresponding exponential form. So this is x equal base 5 logarithm of 7. A logarithm is a power of the base, and so x must be a logarithm, and it's the base 5 logarithm of 7. So the idea here is, though this is not a beautiful number, we know that this number will exist between 1 and 2. That is, 5 to the 1 is 5, and 5 to the 2 is 25. So 7's between those two numbers. But we would anticipate that the logarithm would be closer to 1. And so, of course, we could use our Google calculator to get a nice approximation. Or we can just say, we know what this is now. This is base 5 logarithm of 7. So that's just kind of a, you know, highlight of where we're going. So if you remember this, fine. If not, I'll say more about this. So that would give us the intercept here, the x-intercept. So where we're headed is just to do some reviews so that all of these ideas make more sense to us. Now, when you look at some of our, what do we call these, distinguished bases? For instance, you look on your Google calculator and you see E's and you see LNs and you see LOGs and things like this. So why is that? I mean, why isn't there a subscript for the base? Well, we have two bases that occur often in our work, or at least as humans. We have the base 10, which is the base of our number system. And then we have the the natural base, which we symbolize by E. So remember, pi is a Greek letter. You'll get used to this when we do trigonometry. You have to use pi from the Greek alphabet in your WebAssign table when you actually input things. This can be approximated 1416. Those are the first four decimals of pi. Srisvana Ramanujan could recite as many digits of pi as you like. He was the great mathematician who just did wonderful things like Newton. Didn't live long enough to see all of his work come to fruition, but was an amazing genius. So when we need pi, that's what we need. If an approximation is requested, that's fine. But this 3.14 does not equal pi. It never will. So if you're doing an exact answer, you must use the Greek letter. Now, again, say you're doing a problem where you're doing an exact computation, say away from the geometry, that involves the natural base. Well, the natural base can be defined in terms of a limit. We can let n pass to infinity. And this is a very famous sequence. And you're going to think this looks like compound interest, Professor Ron. 1 plus 1 over n to the nth power. So this is a very famous sequence that actually is monotonic increasing. That is, it's bounded and it increases ever so slowly. And by the monotone convergence theorem, it actually has a limit, and the limit is actually E. And then, of course, if we were wanting to get some type of numerical estimation, it can be computed to whatever decimal place accuracy you want. This is a calculus exercise, 2.7182, etc. So these numbers are both deemed transcendental. And we encounter them so often, we give them special names. That's special symbols. Pi for this number, which we interact with in geometry and calculus, and E for this number, which we interact with mainly in analysis and calculus, and so much in finance. I mean, we're stuck with these two, and there are an uncountable number of each of these types of numbers called transcendental numbers, but we really just spend most of our time with these two. So again, there are other numbers out there, but I don't think anyone has found a great use for them yet. Maybe some of you will find other numbers that will be of use to our computations. So what I wanted to do, again, when we get to the logarithms, I want to remind you that when we have base 10, the corresponding symbol for the logarithm will be log instead of log subscript 10. And when we get to logarithms, which will be soon, the corresponding base E logarithm won't be written log base E, it'll just be written ln for natural log. So these notations have been adopted because of the frequency of use, and they have stuck. So we can't change them. They are as universal as these symbols are, okay? And we're stuck with them. So if you want to change it up, don't think about it. Change something else. So now what I want to do is just to show you how we can actually use this limit definition for the natural base to get what we call continuous interest. This is a nice little simple calculation that we thought a lot about passing to infinity. When we've done dominant terms with polynomials, and then when we've done vertical asymptotes and horizontal asymptotes, so why not go ahead and do some with this? So continuous interest means that n, the number of compoundings, passes to infinity. We think of continuously compounding, not for 12 times a year, but every second of the day. But we don't get the pot of gold because of this limit here, but it does improve the interest, even though most banks don't use it. So the idea is, if that happens, the limit as n approaches infinity, we say, well, we have p, and then we have 1 plus r divided by n raised to the nt. Now, this is just a bunch of algebra, but the limits are very intuitive here, like we've been doing from the beginning of the course, and I want to use that to do this. Notice we want to be able to rig everything so it looks like 1 plus 1 over something to a something power where these two expressions are the same. So what we're going to do is first, we're going to factor the p since it's just a constant and take the limit as n approaches infinity. Now, I want a 1 in the numerator, so I'm going to write r over n is 1 over n over r, like this, n divided by r. So it's like saying 2, I'll write it this way. Let me write it this way. I'll write a fraction. So if I had 2/3, but I wanted to write it with 1 in the numerator, I would just say 1 divided by 3/2. That's basically what I've done here. I've taken r over n and written as 1 over n over r, which is basically the same thing as looking at a fraction 2/3. So that's what I've done here. And then we're thinking, okay, well, I want the n over r to be right out here. So it looks the same, n over r. But I need nt, so I need the t, but I need to absorb the r, so I'm going to put rt out here using the laws of exponents. So now when I multiply n over r times rt, the r's absorb and I'm left with nt, and that looks like that. And this is that, so these are equivalent. Now you're thinking, we're done, right? We are really, because there's the expression we need that looks just like this. But sometimes at the early stages, we can replace n over r with z. That is, z equals n over r. And notice if n goes to infinity, r being a constant, this would imply or be equivalent to z passing to infinity. So you could actually write this with the z variable to make it look more like that. So you could say p, the limit, as z approaches infinity, and then we'd have 1 plus 1 over z to the z power raised to the rt. But now when we compare these two, it doesn't matter if z is going to infinity or n is, these are the same number, because this is exactly the same computation. That is, z is passing to infinity of 1 plus 1 over z to the z, which is the same thing as we have here. Doesn't matter what letters we use, it's just that now they do the exact same thing. And that's the beauty of using the algebra to transform things. So now what's inside is just e. So we get p, e is the new base, and it's raised to the rt power. So now we just get the continuous interest formula based on using the limit definition for the natural base. So now we have equivalently, we have continuous interest. A will be PERT, P times E to the RT. So when we think about these formulas, we see that just by manipulating the compound interest formula using the definition of the natural base, we can see how the natural base can be tied into finance calculations. So here's another indication that we kind of encounter this magical number and we can't get away from it. Now, what I wanted to do is just do a short computation with this new formula and show you how to use the Google calculator with it. So now here's an example. So we look at this and say we have $4,000 is invested. And then we'll say interest is compounded continuously. Interest is compounded continuously. And we're given if R equals 4%, determine the amount in 6 years. Okay, so determine the amount in 6 years. Again, we've got continuous. So notice here, R again is 4 over 100, which is 1 over 25. T is 6, and we have the principal investment of 4,000. So this implies that A is equal to 4,000 E to the RT. So we have 1 over 25 times 6, or if you will, 4,000 using the laws of exponents, or just basic arithmetic, E to the 6 over 25. And this would be an exact rendering of the actual amount. Again, we have a client and we want to make sure that we give them a good approximation of this. So we can go to our Google calculator. We can clear this out from the last problem, and we have 4,000 times, and we can use our base E here. We're spoiled with the Google calculator, and then use our exponent key, and we want 6 over 25. So we have 6, use parentheses, 6 divided by 25, close. And this will give us a nice numeric approximation. So this will be 5,084, and we're just going to round to the nearest cent. 5,084, 9966, which will give us 5,085 and 0 cents. So what's nice about this is that it gives you an opportunity to see how the actual calculus works with your calculator before you actually do the calculus. The thing that's going on here, ladies and gentlemen, are infinite series. And that's why your calculator works. It is a marvel of mathematics and a marvel of engineering technology that we have the electronics that can basically give you a handheld computer to do these computations, just like your cell phone is a handheld computer. And so we get the benefit of being able to utilize the mathematics in a way that is convenient and accurate. And so again, we have exact calculation, and a lot of the problems that you'll do with equation solving, you will enter an exact calculation. Then WebAssign will ask for you to approximate your calculation exact value. So I want you to get used to doing that. But you be happy with your exact calculation, because you know that's the most important. Anything else beyond that is not, because your estimations or your approximations don't mean anything if this is not correct. Then you're just really wasting your time. Now, before we get to the logarithm, there's a nice example here in your WebAssign, and then of course there'll be some examples that I'll hold off on doing until we have the work from Thursday, so they make more sense. But we've got a little example here of a bird population. Again, before we had the fish population. And when you study more mathematics, maybe the differential equations, we're going to do some models next week, which actually fall into the subject matter of differential equations, models that are similar to this. This particular model will be the logistic model. We'll do growth and decay model, instantaneous growth and decay, and Newton law of cooling next week. And this is a similar model, logistic model. But we like to start with those when we're doing modeling in pre-cal, and then when you get to differential equations, you can do the logistic model. Now, what does the solution curve look like? In this case, the population N of t, t will be measured in years. T measured in years. And so we're going to say the bird population has this solution curve, 6,750. And I've converted the decimals to fractions at least, but not the power of the exponential. That's really not as important. These other numbers, we need to have them clean and easy to use. And this is 26.5 when it was listed in the WebAssign. But 26.5 is 26 and a half. So that will give you 52 plus 1 or 53 over 2. So I went ahead and converted these to make our arithmetic easier. 53 over 2. And then we have this exponential term, e, and the power is negative 0.043, and then we have the t. So now what we see is we have a very interesting curve here where you've got this coefficient of the t here that again, you know, you think you're replacing t with something negative, so that does a y-axis reflection for this particular object right here, not for the whole thing. And then you're going to replace t with something smaller, a coefficient smaller between 0 and 1, which is going to cause a stretching horizontally. So this is kind of a little complicated object right here, but it's going to be easy for us to actually manipulate. It won't be the source of any difficulty here. So what I want to make a comment about is, notice this number here is fixed, this is fixed, and so you're thinking there must be some kind of asymptote going on here, because notice this particular function right here is decreasing. This exponential is a decreasing function in the sense that as t gets larger, this particular exponential gets smaller and smaller. So as we look at this particular function here, the denominator is getting smaller as t gets larger. So t is 0 and larger. So this implies that n of t actually increases. If you keep dividing by smaller and smaller numbers in the quotient, the output of the fraction will be larger. So n of t increases since 53 times 2e to the negative 0.043t decreases. So we're actually dividing by smaller and smaller numbers, the number 6,750, as t gets larger. So this pretty much tells us that eventually this thing's going to fade away to 0, because we know that y equals 0 is a horizontal asymptote. So as t gets larger and larger, this is just going to fade to 0. And then we will get some type of limiting value for the actual population. Now, the first question, so this is a little aside here, just using the basic ideas that we've reminded ourselves about the exponential function. Now, again, think about it this way. When you get to calculus, you'll be doing the similar type of analysis, but you'll have more understanding of the exponential. Now, the first calculation is, what is the initial population? Initial population is what? Well, that just means how many birds are there when t equals 0? And that's easy to do. So we get, replace t with 0. So 6,750 divided by 1/2 plus, so we have 53 over 2. And then, of course, we have e to the 0 because t is 0. But remember, e to the 0 by definition is 1. So we get 6,750. And then we have 1/2 plus 53 over 2. Because again, this is 1. So that gives us what? 54 over 2. So 6,750 divided by 54 over 2, which is a nice number. That's just 27. So we get 6,750 divided by 27. And so this, I don't know, this looks pretty good. So 6,750, that'll give us 2. Obviously, we know that's 54. We went forwards to go backwards. And so that'll be a 3 and a 1. And if we bring the 5 down, you can see that the 5 times this will give us 135. So 5 is a 135. And then, of course, we have a 0. So that gives us 250. So those numbers turned out to be nice and beautiful there. No fringe. So when we look at this particular model, we see that the initial population when we start measuring time is just 250 birds. And now what we're thinking of is there going to be a limiting population? So if we wanted to sketch a graph, we know that it would have to be rising, but rising to what? We know where it's going to begin, and without calculus, we can kind of guesstimate what we think it might look like, but we need to know whether or not there's a horizontal asymptote. So first we'll say B and C are just looking at the graph. So we're going to say, what's the limit as n approaches infinity of n of t? That is, do we get a horizontal asymptote like we would dealing with rational functions? You know, when the degrees are in line, either equal or, you know, the degree upstairs is less than the degree downstairs. So what do we get here? So we have limit as n approaches infinity of 6,750 1/2 plus 53 over 2 e to the negative 0.043t. Now, of course, again, this is a decreasing function. We've already talked about this. So intuitively, this part here, this part of the expression gets closer and closer to 0. So in the limit, this can be replaced, this 53 times the exponential can be replaced with 0. So that only leaves 6,750, which doesn't depend on t, and the 1/2. And of course, we get the 0 because in the limit, that converges to 0. Again, it decreases. And we know it decreases to 0. Might as well go ahead and say it. And so now this is just what? 2 times 6,750. So we multiply by 2, so we get what? 0. We get another 0, a 1, and then a 13, carry the 1. So we have a limiting population of 13,500. So what I thought was good about this problem is that just using basic ideas about these functions without the advent of calculus, even though we're doing intuitive limits, they're all limits that make sense to us in the sense that intuitively, when you do calculus, not only do you want to back it up with the correct calculations, but you want to make sure that your intuition for the problem is supported by your calculations. And so when you're doing models, your intuition is extremely important because it's going to say, well, yeah, I see this makes sense because as t approaches infinity, this term converges to 0. So I see that the population can never go beyond this number. So this is actually a horizontal asymptote. That is y equal 13,500. So that's going to be very helpful. So when we draw a reasonable graph, we can draw that in as a horizontal asymptote. So if you like, we can mark this as 13,500. So when you take more advanced classes, a lot of the intuition you build up, especially in pre-calculus and college algebra, will come in very handy. And then, of course, we'll just kind of cheat a little bit and mark this as 250 when t is equal to 0. So this is t, and this is n of t. And so the thing is, we start here, and we increase we increase, and then we have to converge up to this line. Now, of course, this is kind of a guesstimate curve. We know that the concavity here will have to change because this is going to be a nice smooth curve, and then we have to approach this horizontal line. So what's going to happen to the population is that it will increase from 250, given that all the conditions are stabilized, and never pass beyond this. So there might be limitations in the environment that will keep tabs on the population. And sometimes this is important, especially when you're trying to keep a certain species from overrunning the environment. You don't want your setup to be such that you're trying to have a resort village and you've got so many birds that people can't walk around without getting attacked. So this model really does exemplify a lot of the standard characteristics of our exponential functions, and in this case, the natural exponential. So again, I wanted you to look at this as a way to utilize intuition and to use the basic construct of the exponential function to learn something about populations and also about models that we're going to cover some more of next week. Again, we can do a whole lot without the calculus, but we are limited. It's good to start somewhere. Now, what I want to do is say a little bit about our transition to logarithms. Now, this is a simple transition, but what we want to be able to do is just utilize what we already know from the exponential. So I just did a little summary here, and then we'll work through some of these examples. Again, we're making the assumption that our intuition is saying that this exponential function, a to the x, is 1 to 1. That is, when a is bigger than 1, the outputs get larger and larger. And when a is between 0 and 1, the outputs get smaller and smaller. And in both cases, the horizontal asymptote is y equals 0. So this helps us to define the inverse function. And we're going to call it the base A logarithm. The base A logarithm is defined as the inverse of the base A exponential function. So just like we had before, the only new thing I've done here, and you don't have to draw in the blue function if you don't want, I just added it. We now see that the horizontal asymptote for the a to the x will now become the vertical asymptote for the inverse function. And the 0.01 becomes 1, 0. And then, of course, using the symmetry line, we can sketch the actual inverse function for free. So we get again, if the function f is increasing, so does its inverse. They do the same thing. They have to, but we see that this function doesn't get big as fast as this one. That's just the nature of what's going on here. But that's a very nice proof to do that if a invertible function increases, so does its inverse, and it's actually not very difficult. You can actually do it by contradiction. But the thing is, ladies and gentlemen, is that since we know that the range of the exponential function is all positive real numbers, we know the domain of the logarithm will be all positives. So again, that's why we have to be very careful with logarithms. You cannot take the logarithm of an argument that's 0 or negative. They must be positive. So this is even more restrictive than the square root function. Again, we have to be extremely careful when we deal with logarithms. Positive arguments are required. And now, of course, the domain of the exponential function is all reals. So now we see that the logarithm range covers all reals, but it does take its time to cover through all the real numbers. So this is why we can see, ladies and gentlemen, by adopting the same independent variable, we can graph both functions. Even though the logarithm is just the reverse path, it's just the reverse path, we like to be able to graph them on the same set of axes. Because if you look at this is the same function. If I turn it around this way, the logarithm function is right there. Let's see, what would I do? I can't do reflections. I mean, that's the sad part. I can rotate and do the reflections, but if you rotate this function here, pi radians, let's see here, let me see how I can do that. That'll come here, yeah, and then reflect in the y-axis. So if you rotate this function here, pi over 2 radians, it's going to come out this way. And then when you reflect it in the y-axis, you get this. So I can make this look like this. So there is nothing new here. It's just that we write these with the same independent variable and graph them on the same set of axes and then get that nice symmetry property, because it's very much to our advantage to write down a new function for the inverse. This implies this, and this implies this. They are both equivalent. But we are greedy as mathematicians and STEM people. We want to have our own object to manipulate, and it works out very much in our favor, as the history of mathematics has proven to us. So the only other difference here is, remember, with the decreasing exponential function, again, we get the new 0.10, but now we're actually approaching the x equals 0 from the positive infinity sense. So now the natural logarithm in this case looks like this, and of course we've got the symmetry line going on. So we don't spend as much time with logarithms where the bases are between 0 and 1. We really spend more time with e and 10 and 2 and 3 and things like that. So we probably spend more time with these, not to put any less emphasis on these. I just want you to see what it looks like. So again, you can move the logarithm around in the same way. You can shift it around. You can reflect it just like the exponential functions in the same routine that we've been doing. And WebAssign will give you some practice on that. So now what I want to do is just focus on the equation defining the logarithm. We've talked about all the graphical aspects, but what is the logarithm? Well, we define it as the inverse of they say exponential. So for instance, we say y is equal to the base a logarithm of x, if and only if x is equal to a to the y. What does that mean? Y is the power of the base. What is the power of a that equals x? It is y. A to the y equals x. So again, what is a logarithm? It is the power of the base. It is the power of a that equals x. That is a to the y equals x. So when we go backwards, instead of inputting the power, we're going backwards and we have to figure out what it is. And that is a more complicated process in general, even though you would think it would be very simple. So we think of, in this case, the logarithm as being a power of the base. So now what we can do is do some basic simple calculations. Now you're thinking, is it always easy to find the power of the base? Maybe, maybe not. So for instance, note a logarithm is a power of the base. And then we say, in some cases, this is easy. In some cases, this power is easy to determine. We can always figure out where it lives, and then we can use our calculus to approximate it with the Google calculator. But in a lot of cases, it's easy to determine because the input is simple. So here's an example. Let's say we're looking at the base 6 logarithm of 1 over 216. So again, what we want to do is find the power of 6 that equals that. But now we can just do some side calculations here. Let's observe that 6 cubed is actually 216. That is 36 times 6 equals 216. So the power of 6 that equals 216 is 3. So we can go ahead and write that. That's going to be very useful. So the base 6 logarithm of 1 over 216 is the base 6 logarithm of 1 over 6 to the third. But now, of course, we can use the laws of exponents because we're lazy. This will be the base 6 logarithm of 6 to the negative 3. But now the input is a power of the base. And what is that power? It's negative 3. So the base 6 logarithm of 1 over 216 is negative 3. Why is that true? Because 6 to the negative 3 equals 1 over 216. So basically, we just did this, and then we say the same thing again. So we call this the logarithmic form, and we call this the exponential form. What's the logarithm? Power of the base. What power of 6 equals 1 over 216? Negative 3. So we may find this form to be convenient. We may find this form to be convenient, but they're equivalent. So one says the other. So if I look here and say, okay, I look at this and say, oh, negative 3 is a power of the base. It's a logarithm. It's actually negative 3 is actually the base 6 logarithm of 1 over 216, which is exactly that. So which direction you want to go and which form you like is a matter of personal taste. And basically, what is the problem asking you to do? Theoretically, we can always do this. That we may stop with a symbolic gesture of the actual logarithm will be because we want to keep it exact, and an approximation would mar our calculations. But once we get to the end of the problem, as we see with the finance problems, we can make a nice Google scientific calculator approximation. So now here's another example. Notice we didn't have to use any calculator for this. And this is what WebAssign will ask you to do. It'll say compute these logarithms using the definition. Now, what about the base 8 logarithm of 4? And now it's not as simple as this, but we can look at this and say, okay, is it possible to write 4 as a power of 8? And I think we can do it. Just first, let's just observe that the 1/3 power, that is the cube root of 8, is equal to 2, because we know 2 times 2 times 2 equals 8. That is 2 to the third equals 8. But that's convenient because if we square 2, we get 4. And also 2 squared equals 4. I mean, you can run this out anyway. It really doesn't matter how you do it. And then you're thinking, okay, well, we can rig this together and say, well, this will be the base 8 logarithm of what? Well, we have 8 to the 1/3 raised to the second power using this. So this says the base 8 logarithm, and now use the laws of exponents, 8 to the 2/3. But now we have exactly what we have here. That is, what power of 8 equals 8 to the 2/3? Well, 2/3. So now what does that mean? This just says that 8 to the 2/3 equals 4. Even though we just said that, we'll say it again in another way. So again, logarithmic form, exponential form. So really, the only thing here is just remembering that the reverse path requires us to find the actual power. We're trying to find the actual power for the base to get the desired input. So this is called the reverse path. And it's not difficult, except the calculus, since we've got all these numbers in between all these pretty numbers that aren't pretty, we have to say, okay, well, we've got this nice continuous function that covers all these I'll say non-user-friendly numbers. And so we don't want to leave them out because we want our curve to be nice and smooth and nice and continuous. So we need that, and we want our contractions to work. We want our cell phones to work. We want things to have nice domains and not domains that have a lot of holes in them, because that would make for bad electronics. So the beauty here is that we can manipulate the definition of logarithm to compute logarithms by hand. Now, I have an example here. For instance, if we know that the domain of the logarithm or the input of a logarithm has to be positive, this can help us compute domains. So here's a simple example. So this is like doing the square root function domain. So we'll say f of x equals, say, the base, I don't know, base 3 logarithm of 4 minus x squared. That's our base 3 logarithm. That's our logarithmic function base 3. And we'll say domain of f is what? So when you look at this, you're thinking, okay, well, we know that the input must be positive. So we know this would imply that 4 minus x squared must be positive. It can't be 0 because the logarithm of 0 makes absolutely no sense. So then we're saying, okay, well, this is just an easy inequality. This is just x squared is less than 4. But now we can use BDs, but since it's so simple, we can just use square rooting and use absolute value. So this will be absolute value is less than 2. That's just a conjunction. So now we've got -2 less than x less than 2. So now we see that the domain of f is just -2 to 2. But again, this calculation is trivial. I mean, this is an easy calculation. Most times we have to work a whole lot harder than this. And there might be a WebAssign problem where you're required to do more work to figure out the domain. And it may involve doing a calculation that's a lot more complicated than this inequality. But the idea is, for this particular function, these are the only real numbers that make sense here. And so this domain is very restricted. And this would be a nice function to study in calculus. So you're seeing that the logarithm functions and the exponential functions have asymptotes, but they are certainly not the asymptotes that we saw, that we computed with the rational functions. They exist for different reasons, and the computation of them don't exist in the ways that we compute asymptotes for rational functions. So that should at least showcase to you that these new functions here are very different, but in many ways very similar, if that makes any sense. We have to exploit the similarities so we don't go crazy, but we must respect the differences. Now, here's an example from your WebAssign I thought was interesting. We have the age of an artifact. This involves some logarithms. The age of an artifact will be given as A equals -8,267 times the natural log. We're going to use the natural log as I spoke of before, of D divided by D sub 0, where D sub 0 equals the original amount of C14. That's a dating radioisotope, C14. And D is the amount of C14 remaining. So when you actually use radioactive compounds, you have to basically be able to determine how much of the radioisotope is actually present, that is relative to the original amount. And so this is where the logarithm scale is very useful, and the models that we work on with radioactive decay, with instantaneous growth and decay, will be very interesting here. We'll do some of that next week. So when we look at this, we'll say compute age if D is 74% of D sub 0. that is, it's decreased. That is, we're now down to 74% of the original amount. So now, just as a little side calculation, 74 over 100, you can divide by 2. So that'll be a 337 over 50. So now this implies that the age will now be negative 8,267 times the natural log. And now we've got the D, which in this case is 37 over 50 times D sub 0 divided by D sub 0. So the natural log of this, you can put parentheses on there if you like, but it's very clear. It's just a fraction, no sums. So this gives us negative 8,267 times the natural log. Of course, the D sub 0 is absorbed, and we just get 37 over 50. So that's the age right there. And we haven't even used any of the nice identities that the logarithm possesses. We're just treating this as a function and using the minimal properties. We will talk about those shortly. But now we're thinking this is exact, but our client says, okay, can you give me an approximation? So we can go to our Google calculator and pull up the screen share, clear out what we had before. And so now we'll use our negative, even though some calculators have an additive inverse symbol that's different from the minus. So this one, it actually works the same. So that's nice, but in some cases it does cause issues. So 8,267, just make sure your answers make sense. If they don't make sense, you have to try it again. And then we have the natural logarithm of 37 divided by 50. So this will give us a nice calculus approximation, and that gives us approximately 2,489.2358. And now when we go back to our calculations here, in this particular case, it says round to the nearest whole number. So this will give us 2,489 years. So that would be the formatting given by WebAssign. So round to nearest whole number. We always have to follow the formatting. This is very important. When you're doing research, you will have to agree on how you plan to round numbers that you compute so that your findings are consistent, so that you do the same throughout a report that maybe you're doing for your boss or maybe for a department. So again, what we see here is that there are many applications that involve the exponentials and the logarithmic functions. And so even if we know very limited things about exponentials and logarithms, we can still utilize these functions in an intelligent way. But what we really want to be able to do is to say, are there nice rules for the logarithms like there are for the exponents? Because you've got those exponential laws and they're so useful and they make our work easy. Do we have the same kind of apparatus for the logarithm? And the answer is yes, and we need to write those down. So I'm going to do another example with the logarithms once we have a little bit more detail down. This second one is maybe a little bit too complicated for what we're doing right now, so I'll hold off on that. And then, of course, we'll use that one-to-one property. But the reason I make the comment is that if we have all these nice exponent rules, what do we have for the logarithm? I mean, the logarithm is the inverse function of the exponential. So wouldn't it have similar properties? And like I said again, I know I sound like a broken record. The answer is yes. So let's write this theorem. So we're going to suppose that x and y are positive. We want to make sure that when we take the logarithms of these inputs that the logarithm makes sense. and we'll just say R will be a real number, and let A be the bases. Maybe we'll need two bases. So we'll have bases A and B, we'll have a real number R, and then we'll have real numbers X and Y that are strictly positive. Now, of course, you're thinking, why are you writing all this down? Won't we tacitly assume that the logarithms are well defined? And I agree with you, you will, but we do this just to make sure that we're thinking correctly. So this is redundant, but we need it. So the first rule that we can get is called the product. That is, the base A logarithm of the product is actually the base A logarithm sum. So we're going to say the base A logarithm of X plus the base A logarithm of Y. Well, that's kind of crazy. That's like, you know, the product, the sum. When you multiply the two exponentials, you add the exponents, sum, multiply, sum, same thing, but it's just written in terms of the logarithm. Amazing. Really is. Logarithms are really a big deal. It's kind of like determinants in linear algebra. Everybody thinks determinants are just old hash, just old story, has been. Well, ladies and gentlemen, the Gauss-Jordan row reduction that you learned in college algebra is of immense importance. And that replaced the use of determinants to solve systems. But the determinants have such a valuable theoretical impact on mathematics that they're not going anywhere. So all the naysayers can be horrible to the determinants, but we need them. So the quotient rule, you're thinking, well, won't this be redundant? Well, we're going to be redundant again. We're going to say the base A logarithm of X over Y is now the difference of logs. So again, this mimics the rule for the exponent laws. We subtract the exponents, so to speak. What's a logarithm? Power of the base. These are powers. You subtract them. So like I said before, we're not losing anything. We're just writing these in terms of the base A logarithm. And the third one, which is actually one of the most important, is called the power rule. When you get to calculus, you'll have differentiation theorems that use these descriptions. And so you're going to have to really be careful what you mean by power rule. Are you talking about derivatives? Or are you talking about a logarithm identity? So when you take the base A logarithm of X to the R, you're thinking, okay, what's that going to do? Well, this is going to be just like a special case. An exponential function will be a special case of this. And so what should happen is that the R should be able to slide down to the coefficient, and it can. So R base A logarithm of X. Now, before I write the last one, I want to go ahead over here and write the inverse rules, which I didn't write down before I do the last one. Remember, the base A logarithm of A to the X is X. Remember, you compose the two inverses, the input equals output, for X a real number. And then, of course, A composed with the base A logarithm is also X. Input equals output when X is positive. So I might as well go ahead and put these on the same page just to kind of summarize them. Again, remember, we've already learned this, but why don't we go ahead and write them down for the specific functions we're working with? That is, when you compose a function with its inverse, you get the identity. And this is very useful. This is kind of how you can think about logarithmic and exponential form. You can think about applying inverses, or you can just think about the definition of logarithm, but they're all saying the same thing. So the inverse rules we assume, but I'll go ahead and put them on the same page so you'll have these that you can easily put on a note card. And then, of course, the last one is probably one of the most important. It's called change of base. Now, when you take calculus, you learn the calculus of the natural base, the natural logarithm, and then you change all the other bases to the base e. So you get the calculus for the other bases for free. So that's where the use of calculus is very efficient. You don't have to have different calculus for every base. You just simply substantiate it for a very famous base, the natural base, and then convert all the other bases to that base, and you got the calculus for free. So there was really, you know, a beautiful unification of these transcendental functions with the calculus. So how does this go? This would say that the base a logarithm of x is now the base b logarithm of x divided by the base b logarithm of a. And you're thinking, that's crazy. Well, here's the deal. If I want to change from a to b, I just simply replace a with b, and then downstairs I have this change of base factor, which is the new log base of the old. And you're thinking, okay, do I believe that? Well, we can actually prove that, and you don't need calculus to prove it, but, oh, sorry, I just mowed right through the B. This is something we can actually bank on now, and we don't have to worry about it later. The proof we do here in this class will be sufficient. So basically what this says is that if you want to change the base for a logarithm, you physically change the base to the new base, and then you have this change of base factor in the denominator. So a lot of times, like I said before, say we have maybe a base 3 logarithm, and we want to change to the common base, base 10. So we just say log of x. Again, we don't need the 10 because the base 10 log has no subscript. And then we say the base 10 logarithm of 3. So that would be how we would change the base 3 logarithm to the base 10 logarithm, or the common base. And then, of course, in calculus, we do this. We say if we have some base, any base a, we change to the natural base by just writing ln of x, and then we take the natural log of the old base. So this is what we spend time doing in calculus, and we write all of our differentiation formulas and integral formulas using this change of base. So again, this is the key that transfers the calculus of the natural log to any base. And so we automatically get the calculus for our base 10, our common logs. We automatically get the calculus for any base that we want to use. Now, something that I actually haven't done yet is maybe use the definition of logarithm to solve some very simple equations. That's what we're going to spend time on Thursday. We're going to use some of these to do some basic computations, and then use the power of this with the definition of logarithm to solve more elaborate equations. So remember, y equals the base a logarithm of x if and only if x is actually a what? A to the y. Logarithm is a power of the base. And so this is kind of the recipe that defines the base a logarithm dependent upon the base a exponential. So let's just look at some very, very, very simple calculations here. Say we had something like the base 2 logarithm of 3x plus 1 equals, and if you like, we'll just put a 2 here. Now, when you look at this and you think about this standard equation, you're thinking, okay, well, what's a logarithm? It's a power of the base. And so we see that the power of 2 that actually equals 3x plus 1 is 2. So we think, okay, what's the equivalent exponential form, just like we were doing when we were computing logarithms? We'll say 2 raised to the second power is actually equal to 3x plus 1. So the power of 2 that equals 3x plus 1 is 2. So 2 to the 2 equals 3x plus 1. So we have 4 equals 3x plus 1. So 3x, well, you could have done this in your head. You didn't need me for this. 3x equals 3, so x equals 1. You could look at that and say, well, I know what works. 1 works. Well, we want to make sure we get everything. So even a simple equation like this can be solved using the definition of the logarithm. So the idea is what we're interested in is making sure that via this process, we cover all the possibilities. But this is a very simple equation which can be solved just by writing the equivalent exponential equation. So there's something about logarithmic equations that can be extremely simple, but again, we do this every time. Regardless of how much work we have to do, this has always got to be transacted in some way if we have logarithms. Now let's try another one. So what I want to do is make sure before we start on Thursday that you just have the basics down. So look at this equation. Say we have 3 to the x minus 2 equals, I don't know, let's just say 5. So we've got an exponential equation. That is 3 raised to the x minus 2 power equals the real number 5. And of course, this does make sense. I could write down an equation that has no solution, but I won't always do that. We want to see what we can do with this. So now we're thinking, okay, I can't really do much with this because the x minus 2 is an exponent of 3. But I can write this in the corresponding logarithmic form. What's a logarithm? Power of the base. The power of 3 that equals 5 is x minus 2. So x minus 2 is the base 3 logarithm. So x minus 2 is the base 3 logarithm of 5. Now, of course, just like before, this number is between 1 and 2. That is, we know 3 to the 1 is a lower bound for 5, and 3 squared is an upper bound. So we know the base 3 logarithm of 5 exists between 1 and 2, most likely closer to 1, even though the scale is not linear. It stands to reason that this is a computation that we could approximate. And then, of course, x will now just be 2 plus the base 3 logarithm of 5. And that's an exact solution. So we have 2 plus the base 3 logarithm of 5. So what we can see here is that just the basic concept of solving very simple equations simply is adherence to the actual what? The definition of the logarithm. Now, in closing, I want you to think about this for next time. For instance, what if I had 2 exponential functions that were set equal? How could I solve them? For instance, look at something like this. We're going to talk about the one-to-one property. Say we had something like 1 over 16 to the 3 minus x equals 8 to the, let's see, 2x minus 5. For instance, if I wanted to solve this, you're thinking, well, I don't really want to use this, and I really kind of need to use maybe the one-to-one property of the exponential functions. And then it's like I do have a logarithm, but these are all powers of 2. That is, 8 is a power of 2, and 1 over 16 is a power of 2. So I should be able to solve this. That is, 1 over 16 equals 2 to the negative 4, and 8 equals 2 to the third. So this will be 2 to the negative 4 raised to 3 minus x equals 2 to the third raised to 2x minus 5, just keeping those parentheses there so you don't forget them. And then you're thinking, okay, this is 2 to the 4x minus 12, just distributing the negative 4, equals 2 to the 6x minus 15. But now the bases are equal, and these functions are 1-to-1. The exponential function's 1-to-1, so this says 4x minus 12 must equal 6x minus 15. So if I add 15 to both sides, I get 3. And if I subtract 4x from both sides, I get 2x. So x is 3/2. So indeed, if I think about equality of exponentials, I don't even need the logarithm. That is, I get 3/2 as a solution because I was able to write the bases as equal, just because these particular bases were easy powers of 2. And then you use the laws of exponents, that is to get the -15, the 6x, the 4x, and the -12. And then this is what, 1-to-1. If 2 outputs are equal, then the inputs must be equal. So this is just using basic 1-to-1. So this is a very special case when we can align the bases. But what we're going to have to do is, when this is not possible, we're going to have to change up things. We're going to have to apply some different techniques. And now we may have to go back and apply change of base. And we may have to come up with a change of base for exponentials just to be on the safe side. So what I want you to do for next time is go ahead and finish up your work on the polynomials, and then start looking at the work on the exponents and logs. This is a lot easier than the polynomials, you know, because it just makes so much sense. And I think you'll enjoy this. So get that completed, and then start working on the logs. And then on Thursday, we'll talk about more ideas with the identities here, and then solve some more elaborate equations that will take these ideas to a higher level that will allow us to solve more, like I say, complicated equations. Well, I hope you have a good day. Thanks for your attendance today. And if I don't see you at the office hours, I'll look forward to seeing you on Thursday. Everybody have a good one.
Me too.
Bye.
Bye. My favorite class. But don't let that go to your head now. This is my favorite class, but that could change. You have to be kind to Professor Ron. Everybody's so mean to me.